All right, the next speaker is Dr. Björn Paulsson from Paulsson Inc. Maybe we run the video one more time, Lotta.
I could go here and I'll share the video right after his presentation here, since he already shared his screen.
Thank you,
Björn.
Go ahead, Björn.
All right, the famous mute button, unmute button. Yeah. Can you hear me and see my presentation?
Yes.
Okay, thank you. Well, actually, I've been in the oil industry for a number of years, but my first love, if you can call it that, in the energy field is geothermal. I worked on hot dry rock and geothermal energy in Sweden before I came to the United States, 1974. So that's 50 years ago. It kind of tells you how old I am. So we'll talk about effective development geothermal resources using fiber optic multi-sensor arrays. And let me see if I can. So today's talk, geothermal grade sensors from our company. They are now operational at 320 Celsius. And I'm not aware of any other sensor which is higher temperature than that. So I think we're leading the field in high temperature sensors, period, and fiber optic sensors in particular. And in the future, we have designs we can take that temperature up to 500 degrees Celsius. And that matches what Susan was talking about, the super hot geothermal reservoirs at somewhere between 450 to 500 degrees Celsius. And the sensor array technology I will talk about, the vectors 3-component seismic sensor arrays. This is very different than the distributed acoustic sensor arrays, which are becoming fairly common today. These gives you the vector of the incoming seismic energy and basically place in three-dimensional space where the seismic acoustic events you record are located. We deploy the arrays today with 960 sensors simultaneously, which also I think is the world record in terms of a borehole sensor ever being deployed. Acoustic sensor array, we deployed 2,500 sensors for PG&E monitoring underground gas storage. Those sensors have now been operational for 3 years, down to 5,400 feet. Temperature sensor in the same borehole, we deployed 1,800 distributed fiber optic sensor, also been operational now for 3 years. Pressure sensors, a new technology we have developed, laboratory tested. We have not put it into the field yet. We have tested at 200 Celsius, but we can take that also up to 500 Celsius. And I understand, I mean, pressure information is critical to operate a geothermal field. And so that's a very important part of the sensor system. A strain sensor, we deployed 3,000 sensors and monitored that for several months. So here is what drives it all. It's the center of the Earth is molten core, expected life 4 billion years. I think as long as this planet is inhabitable, we will have geothermal energy. It's always on, but it's complex to subtract. And this is, Susan talked about this particular map. Electric production today, at least in 2019, was 1 million megawatt hours, according to Energy Information Administration, which is, with geothermal, we can produce twice that. So this is an enormous underdeveloped resource. And Susan showed this slide as well. But this is a comparison, geothermal energy versus unconventional oil and gas. In 2019, we drilled as a country 20,000 unconventional oil and gas wells at the cost of 6 billion or 6 million each. Super hot enhanced geothermal systems should match, and actually Susan showed that it will be more economical than unconventional oil and gas. So we are heading towards an economic viable solution. I want to show you a couple of slides on how geothermal fields are being developed for the people who are not familiar with that. we found geothermal energy between plate boundaries. And of course, there are many plate boundaries around the world. The one which concerns us here in California is the one between the Pacific plate and the North American plate. And as we all know, the Pacific plate moves north by 25 to 35 millimeter per year relative to the North American plate. And it creates a number of pulled apart bays in the southern termination of San Andreas Fault. And Salton Sea is one example of that. When you're pulling these, let me pull that, you can see that along the San Andreas Fault, it moves and then pulls the crust apart to create a geothermal resource. The pull apart basins were created. Colorado River deposited sediments of millions of years, and the crust is thinned by the pull apart and creates a shallow magma intrusion. That's why they're coming into where the most attractive geothermal energy, because that's where you find the really super hot geothermal resources. And its continued tectonic movements creates faults and fractures. And the key to efficient geothermal production is a detailed map of vertical faults and fractures, which are conduits for water, because you need to get the hot water up to the surface. And only borehole seismic can provide that information in detail. Surface seismic does not see vertical features very well at all, and in a very low resolution. But borehole seismic can go into the boreholes and map where those vertical faults and fractures are, and then we can drill into those vertical faults and fractures to take advantage of the natural flow paths from the hot magma. So summer of Salton Sea is boundaries well defined. It operates in 82 with no major decline. Drilling success 90% within the Salton Sea geothermal field, but underdeveloped. We only produced about 12% of its potential. Power capacity of 22,950 megawatt. We now produce only 350. We fully developed the Salton Sea with almost double the geothermal energy production in the United States. And to boot, we have a lithium resource of 15 million tons, and that's of course where we will what we'll use for generate batteries for storage of energy. So there, the boundary and the operating leases, and 88% left to develop. And here again, Susan showed this picture as well as part of one of her slides, and it produces only steam, so it's a very clean solution. And that, of course, is why it's part of this green connection seminar, because it's compared to coal burning and everything else burning, it's a very, very clean resource. And let me sort of put in context why my company focuses on borehole seismic. If you're looking at the pictures you get from the Earth telescope, that the IEB on the surface of the Earth below the boundary, the atmospheric, which distorts the images from the stars and the galaxies, etc. Compare that left image now with the right image. It's a picture from Hubble Space Telescope, and I'm sure the Webb telescope, the new Webb telescope, is even better than that. You can see that the same picture below or above a boundary which distorts the data is tremendous. And the same analogy, the reason why I'm showing this, because the Earth surface is of course above the near surface zone. The first 1,000 feet basically distorts and attenuates all the high seismic signals we need in order to map the geothermal reservoirs, to map and to monitor them. So the equivalent, essentially, what we are looking at, and I'll show some examples of that later in my presentation. And the fiber Bragg grating, we do fiber Bragg grating. It's an interferometric sensing. It's not Rayleigh scattering like what distributed acoustic sensing is using, which is using a point scattering of Rayleigh scattering. This is an interferometric sensing, and we can sense strains of 10 picometers, 10 to the minus 11 meters. A strand of hair is 10 million times larger than that. A strand of DNA is 2.5 nanometers, or 250 times larger than that. So this is an extraordinary sensitive measurement, and that's why we can record very, very precise measurements with our seismic. This is one of our earlier prototypes of our fiber optic sensors. We're dropping a small needle, 1 centimeter is an equivalent magnitude of -7. We can actually hear 8 hits, and you can see now the picture of the quarter and the needle is I went out to our machine shop and borrowed that's a machine shop needle. So it's a very precise needle, and we drop that 1 centimeter. You can see that the signal we get from that is not only sensitive, but it's also very broad frequency. This is a signal from recording CO2 injected in the carbonate. What you hear here is the sound of fluid flow in fractures. And as far as I know anyway, this is the first time anyone has been able to record the fluid flow in fractures. And this is critical for actually mapping the geothermal reservoirs. We depend on the fluid flow of water in fractures as we bring it up to the surface. We can actually now place where in the rock that flow is happening. And that's will be critical to managing and monitoring the reservoir. And when we plot microseismic events in blue versus the pressure, you get an absolutely precise measurement of or correlation between the events and the pressure. Third generation optic seismic sensors. We have the RXL new sensor, but you saw first was the first generation. This is our third generation. We can now record 20 nanojoule level energies, which is you can see that little styrofoam ball to below the quarter. We're dropping that 4 millimeter and record. We see that signal. We also record data in the field from dynamite shots, 0.65 grams to 2.5 grams, and when we recorded the events in the field, we recorded about 500,000 fluid flows events in 4 weeks and 130 sort of traditional microseismic events. And we also have excellent vector fidelity, which is the reason why that's important, is that now we can reliably detect the direction of the incoming energy and therefore map the fluid flow and the microseismic events. We also tested our sensors in our current oven that goes up to 350 degrees. We tested the sensor up to 320 degrees Celsius, and the next design will do 500 degrees Celsius. So we aim to meet Susan super hot enhanced geothermal system requirements. And this goes up to 0 to 6,000 hertz. And people of you who are familiar with geophone, you're really lucky if you can get a geophone to go up to 200 hertz. And you can see on the bottom right the sensor pod in our oven. We're also not deploying it because it's not only, as Susan said, not just vertical well where you can drop in the cable. We go into deviated wells, and our deployment system is actually designed to go into deviated wells. And here you can see it operates in a small diameter drill pipe, so we can push it out into the directional drilled wells. And we have a full machine shop, so we come up with ideas of what we want to build. We take it to our engineers and say, okay, design this, and then we take it to our machine shop, so we can go from an idea to a prototype in a couple of days, and that's I think is the advantage with having an integrated company doing it, everything from invention to design to manufacturing. And finally, I want to show you a couple of examples of surface seismic. This is a field in the Edison field, actually in Southern California. Surface seismic image, low resolution, no details, no false map. And when we go into borehole seismic, we did 8 well 3D VSP, the first large 3D VSP, I think, recorded in the world. And when we looked at this image, we can map a fault. And then we can identify some oil sands which are not going where they thought were going. We actually see a target, we can map a target, and they drilled a well on this. And that the result from that well was they've encountered 300 feet of oil and became the biggest producer in the field. So not only is it theoretical, it's actually practical that we have implemented this technology. And I think this is my final example. Surface seismic this is BP's Wamsutter field, the biggest gas field in the United States. We did a 3D VSP there with this 160 level, 3 component array, or 8,000 feet long. This is what we got from the surface seismic. This is what we receive, what we're able to image from our 3D VSP data, and we're able to map actually whether residual gas saturation are around that those production wells. So, and we're also developing high temperature pressure sensors, and we can see that using optical technologies, and this of course is what's very important, because pressure is what drives the production. Either you pump it out, or you're driven by natural pressure from the reservoir. And we can see that we tested it at four different temperature, up to from 117 degrees Celsius up to 200 degrees Celsius, and we get an absolutely linear response to our pressure sensors. And conclusion: successfully develop cost-effective, sustainable geothermal energy. We need to first identify geothermal resources. We do that by and large from surface mapping, thermal conductivity, thermal gradients, etc. And then what we need to do is to put high-resolution borehole instruments and technologies to image and monitor the geothermal development and production. So thank you so much for your attention, and I'm open for questions.